Hey there, welcome to NASA Launchpad. I'm your host, Vince Whitfield. Check this out. Today we're going to be talking about how this works, and some other cool stuff Bernoulli did. Oh, that's Daniel Bernoulli, the Dutch-Swiss mathematician known for, that's right, the Bernoulli Principle. Remember Bernoulli's Principle? If you don't, that's okay. Let's check in with JAXA astronaut Koichi Wakata and ESA astronaut Frank de Win on board the International Space Station to review this principle with us. And let's see how Bernoulli's principle can be demonstrated from space.
In a fluid flow, when the flow gets higher, the pressure decreases. And this fact is now well known as the Bernoulli's Principle. If you apply this principle in a fluid flow, in a closed system such as water flow in a tube, if you imagine the tube gets bigger and narrower, the pressure actually decreases when the speed gets higher. And when the speed of the water gets slower, the pressure actually increases. One of the examples that I can give you is that think about the garden hose. And if a water is coming out from the garden hose with a maximum speed, if you still want to increase the speed of the water coming out of the garden hose, what you're going to do is you're going to put your thumb onto the exit of the hose. By doing that, the speed of the water increases, and at the same time, the pressure of the water decreases.
You heard Koichi Wakata talk about water in a garden hose. And yes, Bernoulli's principle deals with fluid, but here's an important thing to keep in mind. Fluid doesn't necessarily mean liquid. Fluid is a generic name that applies to substances that behave in certain ways. Fluids flow smoothly and around things, so gases can be fluids, as can plasma, and even to some extent, plastic solids. Let's take a look at another demonstration of Bernoulli's principle, this time showing how it can apply to a gas, like air.
You are placing these containers not so far from each other, about 5 to 10 centimeters. And then Koichi is going to blow in the middle of those two containers. What do you expect that will happen? Because he blows in the middle, the containers are going to move away from each other, or if he's blowing in the middle, the containers are going to come together. Let's have a look. What you can very easily see here is the containers are drifting together. What is happening? Again, the air that Koichi is blowing through the containers has a higher velocity than the surrounding airs. Because of that, the air traveling in between the containers has a lower pressure because it's moving at a higher speed. Because of that, the pressure on the outside is pressing the two containers together. You can also observe this when you're driving on a highway. When you get too close to a truck, for example, that is driving next to you, automatically you will be drawn towards that truck and you need to steer away from the truck. So this is one of the examples as well of the Bernoulli Principle.
Guess what? You don't have to be on the ISS to try this demonstration. Oh sure, your food containers won't stay suspended in mid-air on Earth like they did on the ISS, but try this demonstration with two balloons hanging close to each other. These balloons are hanging from string taped to a doorway. What do you think will happen when you blow gently between the balloons? That's right, they are pulled together. The air moving between them has less pressure than the air on the other side of each balloon. So, they're pushed together. Here's another example that works on Earth and in space. Watch Frank's demonstration with a piece of paper, and then try it yourself.
Right now, what Frank has a piece of paper. It's curved. And what he's going to do is now he's going to hold this paper, and it's curved, and he's going to blow on the top surface of the paper. What do you think this paper will do? Since the paper is curved like this, do you think the paper will come down or comes up? Let's see what happens. As you see, when Frank blows air on the top side of the paper itself lifts up. This is again one example of the Bernoulli Principle. The air that goes on the top surface of the paper has a higher velocity than the air that is underneath the paper. Because of that difference in the velocity, the pressure of the upper surface has a small pressure than the lower surface. As a result, the paper is lifted up. This is a principle, of course, that I have used a lot in my previous career because I used to be a pilot. And this is how airplanes fly. If you look to the wing of an airplane, you see that it's curved, always a little bit towards the bottom. The side on the top side is longer and is more curved than the bottom side. This means that the air traveling on the top of the wing will travel faster than the air underneath the wing, creating a lower pressure and lifting the wing up. This is what we call lift. And because of this lift, we can travel and we can fly all around the world. Not only me, but you as well can travel wherever you want, thanks to the Bernoulli effect.
So there you go. When you increase the speed in a stream of fluid, remember that's both liquids and gases, the pressure of that stream decreases. Pretty cool, huh? Bernoulli's principle relates to everything from spraying your best friend with a hose to flying in an aeroplane. There's actually more than Bernoulli's principle involved when you take off in an airplane, but that's another topic for another NASA Launchpad. Well, that's it for now. Special thanks to our on-orbit astronauts. Until next time, I'm Vince Whitfield. Thanks for watching NASA Launchpad.